Quantum Leap in Electronics at Northeastern University. Date: July 1, 2025. Event summary: researchers at Northeastern University have made a groundbreaking discovery in quantum materials that could revolutionize the field of electronics, achieving a remarkable speed increase of up to 1000% in electronic devices. This breakthrough was published in the journal Nature Physics and is centered around a technique called thermal quenching, which allows a quantum material, specifically 1θs2, to switch between conductive and insulating states at nearly room temperature. Key findings and implications. 1. Speed and efficiency. The new quantum material can operate at terahertz speeds, which is significantly faster than the current gigahertz speeds utilized by processors. This advancement has the potential to drastically improve processing times and the overall efficiency of electronic devices. 2. Material versatility. The ability to control a single material's conductivity and insulation properties means that multiple materials previously required in electronic devices can be replaced, thus reducing complexity and enhancing performance. 3. Stability. Unlike earlier methods that only enabled temporary changes in material properties, the new approach allows for stable conductivity states that can last for months, representing a significant advancement in quantum material research. Background on the discovery. The research team, led by Alberto de la Torre, an assistant professor of physics, utilized controlled heating and cooling, referred to as thermal quenching, to enable the quantum material 1θs2 to switch between its insulating and conducting states. This ability to instantaneously control the material properties is akin to the function of transistors in computers, which have historically transformed technology from vast machines into portable devices. De la Torre remarked on the significance of this technology, stating, "Processors work in gigahertz right now. The speed of change that this would enable would allow you to go to terahertz." Methodology. By applying light to the quantum material 1θs2, researchers were able to achieve a hidden metallic state that was previously stable only at cryogenic temperatures. The discovery of maintaining this conductive state at practical temperatures marks a significant milestone in materials science. Comparison with other research. While Northeastern University is making strides in the thermal control of quantum materials, other institutions such as the University of Wollongong (UOW) are exploring complementary aspects of quantum materials research. UOW's recent findings focus on creating a superhighway for electricity through the quantum anomalous Hall effect achieved via entropy engineering in a one-atom-thick magnetic material. This method addresses the energy efficiency of quantum devices but differs from Northeastern's light manipulation approach. Timeline of events. June 27, 2025. Northeastern University publishes findings on the thermal quenching of quantum materials in Nature Physics. June 30, 2025, the University of Wollongong announces a separate breakthrough in quantum materials relating to low-energy electronics. Published in Advanced Materials. Conclusion. The discoveries at both Northeastern University and the University of Wollongong highlight the significant advances being made in quantum materials research. The work at Northeastern University emphasizes rapid state switching capabilities in a single material, which could lead to the development of next-generation devices that are faster, cooler, and more energy efficient. As electronic devices continue to evolve, these breakthroughs have the potential to transform everyday technology and address pressing global energy consumption challenges. The future of electronics lies in the innovative engineering of materials, and the pioneering research at Northeastern University is a testament to the possibilities within the realm of quantum materials. The discovery of a new quantum material by researchers at Northeastern University represents a significant advancement in electronic speed and efficiency, achieving a potential 1,000% increase in performance. This finding is particularly counterintuitive because it challenges the long-standing notion that electronic materials must rely on traditional silicon-based components and operate effectively only at extremely low temperatures. 1. Thermal quenching method. the technique of thermal quenching allows the material 1θs2 to switch between conductive and insulating states using controlled heating and cooling. This counterintuitive approach suggests that manipulating temperature can yield significant improvements in electronic performance, contrasting with the typical focus on reducing temperatures for increased conductivity. 2. Room temperature operation. The ability to achieve stable conductive states at near room temperatures as opposed to the cryogenic temperatures previously required is another surprising aspect of this discovery. It implies that practical applications for these materials could be more feasible than previously thought. Removing barriers that have hindered the broader adoption of quantum materials in electronics. 3. Single material versatility. The research indicates that using a single quantum material to perform the functions of both conductors and insulators can simplify electronic designs. This is contrary to current practices that necessitate multiple materials and complex interfaces, typically leading to increased energy loss and reduced efficiency. For long-term stability, the ability of the material to maintain its programmed conductivity states for months rather than just fleeting moments defies the expectation that quantum states would be inherently unstable and short-lived. This stability opens new possibilities for the design and function of future electronic devices. 5. Light manipulation. The use of light to control the material's properties offers a novel means of achieving speed at the quantum level. This is counterintuitive, as traditional electronic circuits typically rely on electrical signals for control, suggesting a shift in the paradigm of how we think about signal processing in electronics. 6. Comparison with other research. While Northeastern's findings focus on thermal control, research from the University of Wollongong explores different methods such as entropy engineering to achieve energy-efficient electronic materials. This divergence highlights a counterintuitive reality in materials science. Multiple pathways to the same goal may exist, each with unique applications and implications for future technologies. These breakthroughs signify a transformative potential for the field of electronics, indicating a shift away from conventional silicon technology towards more innovative and efficient quantum materials. The implications of these discoveries could redefine the limits of computing speed, energy efficiency, and the overall architecture of electronic devices. In the recent report detailing the groundbreaking advancements made by researchers at Northeastern University, the focus on the properties of the quantum material 1θs2 and its applications in electronics is noteworthy. While many might focus on the staggering 1000% speed increase and the potential to revolutionize electronic devices, several subtler yet significant aspects of this discovery are often overlooked. Here we will delve into these crucial points and elucidate their significance. 1. Thermal quenching technique. Significance. The thermal quenching method employed by the researchers is a critical innovation. This technique allows the material to transition between conductive and insulating states at near room temperatures, a feat previously only achievable at cryogenic levels. The importance of this can be underestimated. Operating at higher temperatures considerably simplifies the integration of such materials into existing electronic systems. This adaptability means that manufacturers can potentially replace silicon with quantum materials without the need for extensive re-engineering of devices, thus accelerating the adoption of quantum technologies in consumer electronics. 2. Stability of conductivity states. Significance. The ability of the modified 1θs2 material to maintain its programmed conductivity state for months is a groundbreaking achievement. Previous methods that altered conductivity only did so temporarily, limiting their practical applications. This stability opens avenues for developing new types of memory storage and processing units that could retain their states for extended periods, reducing the need for constant power supply and thereby increasing energy efficiency. This could lead to significant advancements in battery technology and overall device longevity. 3. Single material solution. Significance. One of the most profound implications of this research is the reduction in complexity in electronic devices. Traditionally, devices require multiple materials to achieve the necessary conductive and insulating properties, often leading to increased manufacturing costs and design complications. By utilizing a single material that can be manipulated optically, the researchers eliminate the need for multiple components, simplifying the design and potentially leading to more compact and efficient devices. This approach aligns with the trend towards miniaturization in technology, making devices not only faster but also smaller and more portable. 4. Shift from silicon-based technology. Significance. The report emphasizes a pivotal shift away from silicon-based technology, which has been the cornerstone of electronic devices for decades. As the physical limitations of silicon become more apparent, particularly in terms of heat management and density, quantum materials like 1θs2 present a viable alternative. This transition not only signals a new era in electronics but also aligns with the growing demand for sustainable technology solutions. As quantum materials may offer better efficiency and lower energy consumption compared to traditional silicon semiconductors. 5. Broader context of quantum materials research. Significance. The advancements at Northeastern University are part of a broader trend in quantum materials research, as highlighted by the concurrent discoveries at other institutions such as the University of Wollongong. While Northeastern's focus is on manipulating a single material, UOW is exploring different properties of quantum materials that could lead to energy-efficient devices through entropy engineering. This interconnectedness in research efforts ensures a diverse exploration of quantum materials, which could yield complementary technologies that together push the boundaries of what's possible in electronics. 6. The role of light in material manipulation. Significance. The use of light to control material properties is a fascinating aspect that might be easily overlooked. This method not only speaks to the sophistication of the approach but also hints at the potential for integration with optical computing technologies. As data transmission speeds increase, the ability to manipulate materials using light could lead to significant improvements in computing architectures where optical signals replace traditional electrical signals, further enhancing speed and efficiency. Conclusion. The discoveries made by Northeastern University regarding the quantum material 1θs2 are monumental, not just for the immediate implications of faster electronics but also for the nuanced advancements that could redefine the landscape of technology. Each overlooked aspect, from thermal quenching to the implications of stability and the potential shift away from silicon, contributes to a broader understanding of how quantum materials will shape the future. This research not only advances the field of condensed matter physics but also sets the stage for practical applications that could revolutionize everyday technology, making it not only faster but also more energy efficient and sustainable. As we stand on the brink of a new era in electronics, these subtler elements deserve recognition and further exploration. The groundbreaking research conducted by Northeastern University on the quantum material 1θs2, which has led to a potential 1000% increase in electronic speed, presents several key points worthy of in-depth analysis and discussion. Below are 4 valuable points that highlight the significance of this discovery. 1. Revolutionizing speed and efficiency in electronics. The most striking aspect of this discovery is the potential for quantum materials to operate at terahertz speeds, dramatically surpassing the current gigahertz speeds of conventional processors. This leap in speed could revolutionize the performance of electronic devices, allowing for faster processing times and more efficient data handling. Given the growing demand for high-speed computing and applications such as artificial intelligence, big data, and complex simulations, the ability to increase processing speed by such a magnitude could lead to significant advancements across various technological fields. This improvement not only has implications for consumer electronics but also for industries reliant on rapid data processing such as finance, healthcare, and scientific research. 2. A material versatility and simplification of device design. The discovery of using a single quantum material that can switch between conductive and insulating states eliminates the need for multiple materials in electronic devices. This simplification can lead to more compact designs, reducing the complexity typically associated with integrating different materials. In traditional electronic devices, the interface between conductive and insulating materials can create inefficiencies in heat, which further complicates design and performance. By leveraging the properties of 1θs2, researchers can streamline device architecture, potentially leading to lighter, smaller, and more reliable electronics. This versatility also opens pathways for innovative applications in flexible electronics and wearable technology, where space and weight are critical factors. 3. Stability and longevity of material properties. One of the critical advancements of this research is the ability to maintain stable conductivity states for extended periods, lasting for months rather than mere fractions of a second as seen in previous studies. This stability is crucial for practical applications, enabling the development of devices that can reliably switch states without frequent recalibration or failure. The ability to achieve such stable states at near-room temperatures marks a significant milestone in quantum material research and offers a viable alternative to silicon-based technologies which face limitations in heat management and scalability as electronic components shrink in size. This capability enhances the reliability of future electronics and could lead to longer-lasting devices with reduced maintenance requirements. 4. Potential impact on future quantum technologies. The research at Northeastern University aligns with broader trends in quantum technology, positioning it as a key player in the transition from traditional silicon-based devices to next-generation quantum systems. As the field of quantum computing evolves, materials like 1θs2 that exhibit tunable electronic properties will be critical in developing qubits and other quantum components. The findings also complement ongoing research at institutions like the University of Wollongong, which is exploring energy-efficient quantum devices through different methodologies such as the quantum anomalous Hall effect. This collaborative landscape of quantum materials research underscores the significance of interdisciplinary approaches in tackling the challenges of energy consumption and efficiency in electronics, paving the way for advancements in quantum computing, communications, and energy systems. In conclusion, the discovery of the thermal quenching technique and its application to the quantum material 1θs2 represents a significant leap forward in electronics with profound implications for speed, efficiency, and device architecture. The stability of material properties and the potential for integration into future quantum technologies further highlight the transformative potential of this research. As the field continues to evolve, these advancements will likely play a crucial role in shaping the future of electronics and quantum devices. 1. The Manhattan Project 1942–1945. This was a research and development project during World War II that produced the first nuclear weapons. Led by the United States with the support of the United Kingdom and Canada, the project marked a significant leap in scientific and military technology. Key figures included Robert Oppenheimer, Enrico Fermi, and Richard Feynman. The project not only changed the course of the war but also ushered in the atomic age, fundamentally altering global politics and military strategy. 2. The development of the transistor 1947. The invention of the transistor at Bell Labs by John Bardeen, Walter Brattain, and William Shockley represented a monumental leap in electronics, paving the way for the miniaturization of circuits and the modern computing era. This development replaced vacuum tubes and allowed for the creation of smaller, more efficient electronic devices. The transistor's impact has been profound, leading to the proliferation of computers and digital technology in everyday life. 3. The Apollo Program 1961–1972. NASA's Apollo program was a series of space missions aimed at landing humans on the Moon and bringing them safely back to Earth. The most famous mission, Apollo 11, achieved this goal in 1969. The program pushed the boundaries of technology and engineering, resulting in advancements in materials science, computer technology, and telecommunications. The Apollo missions not only fulfilled a national objective but also inspired generations and demonstrated the possibilities of human ingenuity in space exploration. Future outlook: transforming electronics through quantum materials. The recent breakthroughs in quantum material research, particularly those achieved by Northeastern University and the University of Wollongong UOW, herald a transformative era for electronics. With the potential to increase processing speeds by up to 1,000 times and enhance energy efficiency. The implications of these discoveries extend far beyond mere technological advancements. Here are predictions on how these breakthroughs could shape the future. 1. Quantum computing revolution. As quantum materials become more stable and programmable, they will play a pivotal role in the advancement of quantum computing. The ability to control material properties at room temperature, as demonstrated by Northeastern University, will facilitate the development of quantum computers that are not only faster but also more accessible. This could lead to widespread adoption in sectors like cryptography, complex simulations, and artificial intelligence, where traditional computing faces limitations. 2. Ubiquitous smart devices. With the enhanced conductivity and insulation capabilities of materials like 1T2, future electronic devices could become significantly smaller and more efficient. Smart devices could operate with minimal energy loss and heat generation, leading to longer battery life and reduced environmental impact. Imagine smartphones that can run multiple demanding applications simultaneously without overheating. Or wearables that can continuously monitor health metrics without frequent recharging. 3. Energy-efficient electronics. The research from UOW emphasizing the quantum anomalous Hall effect represents a breakthrough in low-energy electronics. This technology could pave the way for devices that require substantially less energy, thus contributing to global sustainability efforts. For example, energy systems could be designed to retain power over extended periods, reducing the need for frequent recharging and optimizing energy consumption across various sectors. 4. Integration of quantum materials in everyday technology. As researchers refine techniques like thermal quenching and entropy engineering, the integration of quantum materials into everyday technology will become more feasible. Manufacturers could replace conventional silicon components with quantum materials in consumer electronics, automotive systems, and industrial machinery. This transition could lead to products that are not only faster but also exhibit unprecedented reliability and performance. 5. New frontiers in artificial intelligence and machine learning. The significant speed enhancements afforded by quantum materials could also revolutionize fields like artificial intelligence (AI) and machine learning (ML). With faster processing capabilities, algorithms could analyze data and learn from it at unprecedented speeds, leading to more advanced AI systems that can tackle complex real-world problems, from climate modeling to personalized medicine. 6. Advancements in telecommunications. Telecommunication systems could benefit immensely from the terahertz speeds enabled by quantum materials. High-speed data transmission coupled with reduced signal loss would drastically enhance internet speeds and connectivity. This could facilitate the rollout of next-generation networks such as 6G, which promise to support the ever-growing demand for data and connectivity in an increasingly digital world. 7. Revolutionizing medical technology. The implications of these quantum material advancements extend to the medical field as well. Faster processing speeds and energy-efficient devices could improve imaging technologies, diagnostic tools, and even targeted therapies. For instance, medical imaging systems that utilize quantum materials might provide real-time high-resolution imaging without the need for extensive preparations or prolonged waiting times. 8. Emergence of new industries. As quantum materials find applications in various sectors, entirely new industries could emerge. The demand for skilled professionals who understand quantum technologies will likely grow, prompting educational institutions to adapt their curricula. This shift could lead to an era of innovation, with startups and established companies alike striving to harness the potential of these new materials. 9. Addressing global challenges. The energy-efficient characteristics of quantum materials could play a crucial role in addressing global challenges such as climate change and energy scarcity. By facilitating the development of devices that consume less power, society can move towards a more sustainable future. This aligns with global efforts to reduce carbon footprints and transition to renewable energy sources. 10. Ethical and societal implications. As with any technological revolution, the advances in quantum materials will raise ethical and societal questions. Issues related to privacy, security, and the digital divide will need to be addressed as quantum technologies become pervasive. Policymakers, researchers, and technologists must collaborate to ensure that the benefits of these advancements are shared equitably across society. Conclusion. The discoveries at Northeastern University and UOW mark significant milestones in the realm of quantum materials and their applications in electronics. As these technologies mature, they will undoubtedly reshape industries, enhance everyday life, and address pressing global challenges. The future of electronics is poised for a quantum leap, promising unprecedented speed, efficiency, and functionality that could redefine our technological landscape.